Good afternoon, everyone. We will start our discussion. Is my voice? Hello. Is there a echoing sound in the voice? Uh, just let me figure it out. Hello. I think it is fine now, right? Is it clear now? Uh, am I audible? Mm, I don't have any other device connected, and this is on mute. But this is already on mute. I'll try that. I'll try. Uh, is it fine now that I have logged out of it? Okay. Maybe I'll rejoin in this device once again. Okay. I think no, it's like um, actually I take the classes always using this setup only. I don't know why it is creating problem today. I think maybe I'll just rejoin once again. I think. Hello. I think it is fine now. Earlier the speaker was taking from the actually mic was different. That's why. Yes. Okay. Thank you. Uh, So, good afternoon, and we will start our discussions on the week 9 content of Smart Grid Basics to Advanced Technology NPTEL course. So, I am Adyasha Sahoo, a PhD scholar from IIT Roorkee. So, in the previous week 8, we discussed regarding the optimal PMU placement problem, the model formulation, and the various algorithms available for solving the problem, classical as well as heuristic based methods. And after that, we talked about cyber attacks and various types of cyber attacks, the cyber anomaly detection techniques. Then we discussed various demand side management strategies and demand response activities. Now, for this week 9, it is basically the hardware demonstration of the theories that we saw previously. Basically, the PV generation, wind generation, how that experiments can be performed in a lab setup. After that, we will see the cell balancing method that we have seen previously in our lectures in theory, how it is done practically in a lab environment. After these three demonstrations, then we will briefly see regarding the control strategy in a hybrid AC-DC microgrid. And then in the uh, next weeks, we'll discuss those control strategies in detail. So for that hardware demonstrations, we will first go through the various components or that we are using in the experiments. So the first thing we have here is a programmable DC source. So this is first we are discussing for the PV generation. So if we want to perform some experiment regarding the PV power generation, and we do not need to rely on a PV panel. So instead of a PV panel, what we can use, we know that PV is producing DC, DC power. So we use a programmable DC source to mimic the performance, uh, to mimic the characteristics of a PV panel. And this emulator allows us to do so. How we can do that? Basically, you can give the various features, various input parameters, such as your open circuit voltage, then your PV power, then your MPPT voltages and currents. And by giving this input, the programmable DC source can generate the PV and IV curves and basically mimic the performance of a PV panel. Now, once you have this programmable DC source, which is equivalent to a PV panel, so for synchronizing it to the grid, what we need, because the PV is a DC source, as we said, so we need to connect it to a converter, right? And what type of converter it should be? So since PV is a DC source and the grid we know is a AC side, so between them we need to have a DC to AC conversion or a inverter with us. So that is this semicron IGBT stack is acting as a inverter for DC to AC conversion. So this is the name of the equipment, the hardware equipment. So Micron is the company, and this IGBT stack basically we'll see this this yellow box is basically the Semicron IGBT stack. Here you can see that it is having, you see here, it is having four legs, as we say. This is the first one, second one, third one, and fourth one. So this stack is consisting of a four-leg IGBT. Yes, basically. Uh, so for each RYB phase, you can use one leg and basically one extra leg you have with you. If you need, you can connect that also. So for the RYB phases, you can connect phase R to this leg, Y to this, and this for the third phase. Now, this is somewhat nothing but, these are switches. So one Each leg is consisting of two IGBT modules, and you have their body diodes across it, and then capacitor across them. This is one leg of the inverter. Uh, Now the next equipment, the grid emulator is here acting as the grid, like the PV panel is being emulated by the programmable DC source. To mimic the performance or characteristics of the grid, we have the grid emulator. So it is acting as the grid side. Then you have a voltage and current sensors to basically uh, uh, we are connecting hardware components for each part of the circuit, right? So for the PV, instead of the PV panel, we have that programmable DC source. Then we placed a physical inverter. Now we cannot connect to the grid which is in the upper side, right? To emulate the performance of the grid side, we have another component, hardware component, that is the grid emulator. So it is in the circuit, I think somewhere. Yes, this Synergia thing, no, this is the grid emulator. Yes, this component will act as the grid. Grid forming and grid feeding converters. No, no. Grid there in the grid forming and grid feeding concept is what when you have multiple basically converters with you, let's say 3 to 4 converters with you, and let's say the micro in a microgrid setup where you have multiple sources and multiple converters with you, and let's say the grid forming type of operation only comes into play when you don't have the grid, basically in the islanded mode of operation. So in the islanded mode, basically all these inverters, they require some reference signals to work upon the control logic. So as long as you have the grid, then they can work in the grid feeding mode. But once the grid is cut off and you are in the islanded mode of operation, so all these inverters, they do not have any reference signals with them, so they cannot function. So what happens is among the available inverters in the system, one of this inverter now acts as the grid forming inverter. So the reference signals for the other inverters is given by the grid forming inverter. So you can say that in that scenario, the grid forming inverter will take the place of the grid, and it will give the reference signal to the other inverters, and the microgrid can function in the islanded mode of operation. Okay. So we talked about DC source, grid emulator, then the semicron IGBT stack is the inverter, and then we have voltage and current sensors. So basically, to detect the voltage and current at the PCC or at any location that you want, and if you want to give that input or information to other parts of the circuit, then need sensors. Then we have this Opalati platform. So this is the basically the real-time simulator. Now, what is this real-time simulator does? So, before implementing any control logic or in the inverters or something, what we do, we first implement it in the software, right? Using this MATLAB platform, you have the Simulink platform where you basically join the components, the various components and switches, and you basically build the system in the software. Nothing is hardware in the system. So you build the whole complete system in the software. You feed in the control logic, and you see whether your system is working fine or not. So once that is done, but here you see there is no physical component involved in it. There is no real-time simulation going on. By real time, we mean that the time taken is basically not according to the practical world, because you're not using any physical assets there. It is just that we see that the control logic is working fine. That is the first step while implementing any technology. Now, once the software validation is done, then we gradually move towards the practical field of deployment. So, in the first step, your software you validated in the MATLAB. After that, what we do, we will then try to uh, basically mimic the performance use implement it using hardware. So that is what we are doing here. So instead of the PV, if in the MATLAB what you do, you will have a PV panel box there and you connect it. So instead of the PV panel in the software, we are using a physical or a hardware component, which is this programmable DC source. Then instead of the converters in the software, you are using the actual physical semicron IGBT stacks. So basically, we are using hardware components in the actual world, and the OpenRT platform here. Though in the OpenRT platform, you just have the test system. Basically, you this is the PCC, and you have your PV, you have the DC to AC conversion, and then after the PCC, you will have some bus system also, right? Connected likewise. So up to here, you are connecting hardware components, but still you do not have the information of this test system. Maybe it is a 6 bus system, 30 bus system, whatever it is, or any practical system. So this test system is embedded in the real-time simulator in the OpenRT. So up to before this PCC, all components are in actual, but the test system is feeded in this OpenRT platform, and then we perform the simulations. So that's why we are calling it as a real-time simulator. Now, if this setup works fine, then what we do the field deployment. Means in the actual system, in the actual practical distribution system, or your actual practical transmission system, whatever is your test system, you go and you connect these PV panels and inverters in the desired bus locations, and you start your system. So that is the last thing. So before that, we do this OpenRT real-time simulations hardware, which we call them as the power hardware or PHIL setups. Power hardware in loop simulations. So this is also a simulation, because the OpenRT, we are simulating the test system, but we have the power hardware in the sense of the other the resources that we need to connect before the PCC. So the in that way, basically, we are Opalati is basically the name of the company. I cannot something real time. Huh. It is a type of real time simulator. Yes, it can be Opalati. Sorry. No, it is basically you feed in. It is a type of software only. You have cards there. You feed in the information of your test system there. And through the cards, basically this hardware and the opalati, they interact with each other. You will give the information from the hardware side to the test system to the opalati, then the opalati gives back to the hardware setup, and those kind of information exchange takes place there. Now this next we have this Texas is again the company, and Texas DSP board, basically here we implement the control logic. So whatever control logic that is coded in this DSP boards. And then you have a MCB, which will act as the PCC. Now with this components, we'll see the circuit. So again, if we see here, we are explaining the semicron IGBT stack. So, what are the components of this semicron IGBT stack? Basically, here, as I said, it has four legs, and each leg is having two IGBT, their corresponding body diodes. Then we have also a heat sink, basically to protect it from the thermal uh, over temperatures or rising temperatures. Then you have the snubber capacitors. So such snubber capacitors are again a protection type circuit. So the role of the snubber capacitor is to protect from high dV by dt transients. So whenever there are such condition is detected, those snubber capacitors are activated to protect the IGBT modules. Basically, what happens is you see. So if high dV by dt condition is detected in this leg, what will happen is this capacitor, it will act as a short circuit. And if it will act as a short circuit, then you have a very low resistive path for the current to flow. So this leg will be bypassed and the current surge will flow through this capacitor. Yes, the circuit will be protected. So this, yes, so that is the function of the snubber capacitor. So these are body diode is for the functioning, no, for the on-off purpose, the duty cycle. So it is for, yes, it will basically depend upon the operation that which set of diodes you are using. So if you want that, you want combinations like you have here one, two, three, four, five, six IGBTs and their diodes with you. Let's say you want for certain operations that 1, 3, and 5 are on and 2, 4, 6 are off. So in that case, for we use the body diodes and in the other case, we will use the transistor IGBTs basically. And then we have this gate driver circuit. So basically, they are giving you the pulses. Basically, the Opel RT or the simulator, it will run the control algorithm. And after the control algorithm, you will get the decision of the pulses or the duty cycle, that what is the desired duty cycle in this current scenario, and then this will be given to the inverter through the gate driver circuit. Basically this gate drive, this pulses given to the gate through the gate driver circuits will be given to this inverter. So it is for receiving the input from the OpenRT platform, information of the duty cycle. Then for this PV generation, we have two type of setups: single stage, or a two-stage setup. Single stage or dual stage setup. So in the single stage setup, we have this PV panel with you. Then you have the DC link capacitor, and then you have the inverter with you, and then you have this grid connection. Now in the dual stage, what we first step up this voltage. No, no. Snubber capacitor is embedded in this inverter. Yes. This is the we call the DC link capacitor. So it is basically used to control the direction of power flow. So if this VDC is greater than this V grid, then the power will flow from PV side to the grid side. If this DC link voltage is less than the grid side voltage, then there will be power flow from grid to PV, which we do not want. So to avoid this operation, basically we control this DC side voltage to be greater than the grid side to feed the power to the grid. And because that is not desirable, no. The control logic basically will ensure that this voltage is greater than the grid side voltage. We always maintain that. Huh. This is the AC side, but we calculate the equivalent DC side voltage, and it comes around in the range of 600, if I'm not wrong, 660 to 660 volts. I think the DC link voltage should be greater than this 660 volt at all times. Okay. Uh, then in the dual stage, what we do basically we boost up this voltage using a boost converter, a DC-DC converter basically, and then we have the inverter, and then we have the grid. So in the two-stage conversion, we have greater losses here because we are converting the power in two stages due to dual stage conversion. Now, the what are in the single stage solar configuration, how it is being done, we'll see that. So for that, we have this MPPT module. So what will this MPPT algorithm does is basically it calculates, basically it will receive the input from the PV panel, the V voltage and current information from the PV panel. And then it will decide that what should be the DC link voltage to extract maximum available power at the VPV and IPV. So extract maximum power for given VPV and IPV. So it will calculate that, and basically you will get the reference for the DC link voltage VDC link star. Now, using this voltage sensor, you will sense the actual DC link voltage, and then uh, you will basically calculate that depending upon the MPPT DC link reference signal and the actual DC link voltage available, what should be the current reference signal, this ID star, and this Q AC star. Basically, and they are then fed into the AC control block. This then will generate the PWM pulses or the duty cycle for the inverter. And this is again a closed loop or feedback type of thing, where again the voltage and current of the AC side are fed into the power and AC control loop, and that is done through a PLL. Basically, this PLL is for the synchronization. So it checks the voltage magnitude and theta at all times so that the system is in synchronism. So with this, basically, we try to extract the maximum available power from the PV for a given operating scenario, basically this VPV and IPV. Now, here as we had seen that the inverter had four legs, right? So for this as so this DC to AC inverter is nothing but for that you will use the semicron IGBT stack. And how many legs of the IGBT module will be used? And for three phase, we are doing three phase here, so it will be three legs will be used. And then here also similarly you have the inverter, so three legs are used up. Now can we for this boost converter, what we need to connect? Either another boost converter, or we'll see that how we can use the fourth leg of the IGBT, basically semicron module, to get the boost converter. So you see the boost converter. This is the DC link. We have the diode and the capacitor. So this is a boost converter, and after that again you have the DC to AC, and then again you have the grid. So, and in this semicron IGBT stack you have one leg remaining, and each leg look like this. So can we utilize these components to get the configuration of a boost converter? Basically, if you see, this diode is in series with the switch, right? So here, if I take T2 as my switch, Then which diode will be in series with T2? Yes, D1. And if I take T1, then D2 is in series. So if I basically, if no, basically these are how the available connections with you. Now, depending upon how you want to use them, body diodes. Hmm. Yes, yes, this. Hmm. Yes. Basically, either you can use T2 and D1 or T1 and D2. Yes. And that will be basically used from the IGBT stack, from the fourth leg. Yes. And here you have used one, two, three legs, and the fourth leg is for the boost converter. One, two, three legs is for the inverter. So the complete semicron IGBT stack is basically utilized for this experiment. Uh, Basically, this A, B points are here, A, B points. Yes, that is a snubber capacitor. Mm. Here. Mhm. This is called as the phase lock loop. So it to check whether the synchronism is in the basically the PV and its converter is in synchronous operation with the grid. So the PLA basically checks the voltage magnitude and theta at all times to ensure that these two systems are synchronized. Magnitude, hmm, and the angle. Yes. Yes, V magnitude, as I said, and the theta. But for theta, we can then vary if it is not in synchronism. Basically, we can use this theta to maintain the synchronism. From the, hmm, hmm. So this was the single stage conversion, and in the dual stage inverter configuration, again, this control is similar to the single stage. So this is same as the single stage solar inverter. With that, when we add the boost or DC-DC converter configuration to get the dual stage configuration. So above that, so this is the DC-AC converter uh, flow diagram, and for the DC-DC converter control or for the boost converter control, what we are doing here basically similarly you are tracking the VPV and IPV, and that you are giving to the MPPT. Again, from this MPPT, you are calculating the reference signal for the PV that is given to this PV voltage control, and again it will basically match it with the actual V voltage with the PV and calculate the reference for the DC link current, and then the DC current control will give the PWM pulses to the DC-DC converter. MPPT mode is basically if you uh, see, you have the curve as something like this, no? So in the maximum power point tracking, what we do is basically uh, the power that can be extracted. Let's say currently the voltage, the at all times basically you have one operating voltage, that is VOC of the panel, and I short circuit. Now the VPV should always be below this VAC. That is, let me write it this way. VOC is always greater than VPV because that is the limit of the panel. And similarly, the PV current should be less than the short circuit current of the panel. Now, to basically maximize the performance of the MPPT to maximize the performance of the PV panel, depending upon the current irradiance level and the voltage and current, what we try to do, we try to basically calculate the reference signal VPV star such that the power output from the PV panel will be maximum. Open circuit voltage. Because that is the limit of the panel. Beyond that is the maximum open circuit voltage available across the panel, and I short circuit current is the maximum current that can be drawn from the panel. So always the you need to operate within those ranges. Yes, always you need to ensure that. Acha, I will see that. Then. So there are four options. Like in the option, both V and I options are there, or only V and only I. Mm-hmm. Yes. Oh, but that is the maximum short circuit current that can be derived from the panel. So I don't think. Mhm. A maximum maybe IMP maximum power. Hmm. Yes, sir. Maybe I'll just. I will check once again that. So this is the final lab setup. So this is the grid emulator, this Synergia box, and this is the DC power source acting as your PV. This is acting as your grid, the grid emulator. Then this box here, this one, That is your inverter or your IGBT stack. Then you have this MCB, which is acting as your PCC. Then you have some filters. So in this way, basically these are connected here. That completes power generation from solar power generation. Now moving to wind power generation. So here we have the DFIG setup, basically doubly fed induction generator. So you see this is the stator power. You are, and through the transformer you are giving it to the grid. And then you have the rotor side power also here as shown. So the direction of the rotor side power, it can be in this way or it can be this way. That means it can be bidirectional. It can be positive or negative depending upon the scenario. What scenario? Basically, the power output of this P stator will not be constant. It will vary because it will depend upon the wind speed. Now, as the wind speed is variable, this P starter will stator current, basically stator power of the induction machine, that will also be variable. Now, to give constant power to the grid, this P rotor is used to match the imbalance between the P starter and the grid. Basically, stator, not starter. So this P stator plus P rotor is equal to P grid. Now, let's say uh, in the subsynchronous mode of operation, what happens is the starter is less than the P grid. So in that case, your P rotor will be greater than zero or it will be positive so that the sum of stator and rotor power is equal to the P grid. And in synchronous mode, what happens is your stator power is exactly equal to the grid power so that the rotor power is zero. And in super synchronous mode, the stator power is greater than the P grid. So the rotor will absorb the excess power and it will be negative. So here rotor absorbs power. In the subsynchronous, it will inject the power to ensure that constant P grid is maintained. Now you see this rotor side is basically connected with the help of this rotor side converter, RSC, and this grid side converter. So we will see what is the requirement of these both converters. Uh, so what happens is basically how the DFIG will work. You have the blades of the turbine here, wind turbine, and wind will flow through this blade and then through the gearbox. It will drive the induction generator. To emulate this part in the lab, we use a DC motor to drive the induction generator. So, to perform the experiment in the lab setup, like in the for the PV panel, we used a programmable DC source. So, instead of that physical blades of the turbine and the gearbox, we are using a motor to rotate the shaft of the generator instead of the wind. So we can control the basically speed of the DC motor to have different wind speed level or different characteristics of the wind. So the output of the DC motor or output voltage, basically the V output voltage output of DC motor is controlled according to the wind characteristics. So, as we saw here, we had a rotor side converter and a grid side converter. First, we will see the rotor side control. So, this is the first block diagram here. So, you see, as similar to the MPPT algorithm in the solar, we have the MPPT control block for the wind also. So, it is getting the input as the speed of the wind velocity. And then the MPPT tracking is done and the reference V wind star is computed. Uh, Basically, the omega for the it is computed and then it is checked with the actual rotor speed omega. So this plus minus means is basically can compute the difference between the reference and the actual rotor speed. And after that, basically, this is nothing but the error, right? Error between the desired speed and the actual speed. So to minimize this error, we use the PI controller. So the PI controller will try to match both this reference and the actual wind rotor speed. And then we have this limiter here. You can see it is 0 to max. Basically, it will limit. Here you can see it is giving you the Q axis reference signal, IQ star. So it may happen that IQ star is greater than the maximum allowable rating of the controller. So we then limit it to the maximum, basically keep this IQ star between the range of 0 to the maximum allowable rating. And then again, this reference of IQ star is uh, compared with the actual rotor side current. And again, we try to minimize this error here in the PI controller and we can calculate the reference voltage for the Q axis, this V star Q. Now, this was the Q axis. Now, in the D axis, we are tracking the frequency here and then matching it with the estimated frequency. Again, we are minimizing this error in the PI controller and calculating here the D axis current ID star. Then we compared it with the actual current of the rotor ID and again we get similarly the voltage reference for the D axis. Now once we got the voltages in the DQ frame, we convert this DQ voltages into ABC frame and these are then given to the PWM generation so that you get the pulses. So that is the rotor side control. Now what happens in the grid side control here is, here you are tracking the DC link voltage, VDC star, and then again you're comparing it with the actual. Similarly to the previous one, you are minimizing the error in the PI controller and calculating the ID star, and again you are comparing and getting finally the VD star for the grid side control. Similarly, in the Q axis you are tracking the reactive current, and basically here you are getting VQ star, and similarly again you are converting it to the ABC frame and getting the PWM signals for the grid side converter. So here basically what you need to remember is, for the rotor side control, in the D axis you are tracking the frequency. For the Q axis you are tracking the wind velocity. In the grid side control, in the D axis you are tracking the DC link voltage, and in the Q axis you are tracking the reactive current. Now, how this DFIG setup is run, basically, you first switch on, supply the voltage using the power amplifier, and then the main and the rotor branch circuit is switched on to charge the DC link. Now, once the DC link has been charged, the next step is to synchronize. So, to synchronize, you enable the phase lock loop to synchronize it. Now, once the DC link has been charged to the required voltage, so you then enable the grid side converter control. After that, what you do, you vary the duty cycle of the chopper, basically to emulate the wind characteristics. Now, after that, once you have gave basically the input to the DFIG, means you are getting now the stator side you will get the power. Now to match the stator side power to the grid side, we have seen that we need the rotor side power. So for that, basically the rotor side control is used to basically build up the voltage and then match the difference, this difference between grid and this stator, using the P rotor. And after that, you synchronize the, basically when you match this P stator with P grid using P rotor, basically you can then go for the synchronization. Now, how the synchronization is done? Once we are ready for synchronization, basically we enable the rotor side control and give the voltage reference signal. If you remember, here in the rotor side control, here you are giving the reference for the frequency, and then we basically try to match the reference, match the stator side voltage to the reference signal, and then in that process, basically both the D control and the Q control, it is done. So the Q control will basically match the theta, and then the D is basically matching the grid voltage. And once both these are matched, basically we can say that the synchronization can be done. Now the next hardware setup was for the, sorry, window machine is, it is squirrel cage. No, it will not be squirrel cage. It will be slip ring because you are varying the rotor side power, no, P rotor. It will be slip ring. Now, cell balancing methods. So we had seen in the previous lectures that the various like a battery pack will be consisting of different cells, and these cells may have different SOCs. So why these they may have different SOC? So cells in a battery pack may have different SOCs due to various conditions such as differences in the temperature, differences in their internal resistance, differences in their leakage currents, differences in operating condition. So due to all these, the cells in a battery may have different SOCs. So what will be the problem if a battery pack, if the cells in a battery pack have different SOCs? So basically, it may lead to issue of overcharging or over discharging a cell. So let's say a battery pack is having two cells, and one is at 5% SOC and other is at 95% SOC. And we know that it is not recommended to discharge a cell below a certain limit and similarly charge a cell with above a certain SOC. So let's say the limit of SOC for safe operation is between 5% to 95%. Then such a battery pack can neither be charged can or be discharged. Can neither, because when you try to charge this battery pack, you are basically driving this 95% SOC cell to go beyond the safe limit. And similarly, if you try to discharge this battery pack, you are trying to discharge this 5% SOC cell beyond its limit. So to avoid such kind of scenario, we need to balance the SOCs of all the cells in a battery pack. So for that, we have various cell balancing methods that we discussed earlier. So majorly they were passive type or active type. So in the passive type, what we were trying to do, we were trying to match the SOCs by uh, basically dissipating the excess SOC in the form of heat. Basically, we discharge the battery using resistors and the power is lost in the form of heat. So that was the passive method. In the active method, what we do, we transfer the SOCs between the cells. Basically, if there are three, four cells, they transfer the SOCs between them to achieve equal SOCs among them. So this active method, you can see it can be cell to cell, cell to bypass, or pack to pack from a battery pack to another battery pack. Now, in cell to cell, it can be again cell balancing method between adjacent cells or between any cell or from direct cell to cell. So first we will see the passive balancing experimentation. So here we have three cells, right? You see, and they are connected in series. So first is from 0 volt to 4.2 volt. The other is from 4, the other is from 4.2 volt to 8.4 volt, and then we have 8.4 volt to 12.6 volt. So this we have three cells in series. Now we have this charger or load, and these are nothing but your switches here. These are the resistors through which you will discharge the power. So what we do here in passive cell balancing is, let's say we have three cells in series. So cell 1, cell 2, and cell 3. Let's say the cell 1 is at 50% SOC, cell 2 is at 55% SOC, and cell 3 is at 52% SOC. And then you have the respective switch and the resistance across it. And let's say you are trying to charge this. So charging means the current will be in this direction. Now, if you want to charge this pack, charge to 60%, then which cell will first reach to 60% SOC? Yes, so C2 will first reach to 60%. Now, as soon as this pack C2 reaches to 60%, what will happen? This switch will on and the power will be transferred to this resistor. Basically, you will bypass that cell so that it is not going above 60%. Now, after C2, then similarly C3 will reach to 60% next. Again, this switch will be on and the power will be transferred to this resistor by bypassing C3 and finally C1. So in this way, basically, you ensure that all the cells are reaching to the same 60% SOC while charging. And a similar operation can be done for discharging also. So C1, C2, C3. This is discharge. So the direction will be this side. This is charge. So let's say similarly, this is at 50%, 55%, 52%. And let's say you are trying to discharge till 45%. So now what will be the sequence here? No, you are discharging to 45. So which cell will first reach 45%? Yes, it will be mm, C1, then it will be C2. But now you what the direction will be this, and due to this only you have, you see here four switches basically, M1, M2, M3 and M4. So you, while charging we are using M1 and M2, and while discharging we are using M3 and M4. So that was passive cell balancing. Basically, we are discharging the SOC through the resistor. Sorry. Mm, no, I think these are these switches are not M1, M2, M3. I think they will be here. These part can be, I think, the switches or these. I'm not sure which one are these switches, but definitely these M1, M2, M3, M4 are not this, which I have shown here. Those will be initially. No, no, they are not the bypassing switch. Hmm. So that was passive balancing, and in active balancing, we have a control hardware in loop setup. So earlier, what we saw was a power hardware in loop. So now this is a control hardware in loop, means that only the control algorithm you are coding in the DSP here. So the DSP is having the control algorithm, but all the other things, your converters or the switches, batteries, everything is in the OPLRT except the control algorithm. Battery and other, they are embedded in the OPLRT system. So due to this, this is a control hardware in loop setup. So you basically code the control logic in this DSP board, and then you give that DSP signal to the OPLRT through your DI port of the OPLRT, and then the OPLRT will basically give that pulses to the battery and other things, and it will then give back to the DSP board. So here basically you see, first we'll see this. So what we are monitoring here, you see there are three SOCs. You have the load power, discharger power. Then you have this duty cycles D1, D2, D3, and the current information I1, I2, I3. So you are giving the input, but so this voltage level here is 3.3 volt. So what we do when we give the signal from OPLRT to this board, we ensure that everything is scaled down to 3 volt so that the board is not damaged. Now this is active balancing means we are doing the doing the cell transform charge transfer from cell to cell. How we do that? That is through the average standard deviation algorithm. So what is this? We will see. So let's say you have two SOCs, two cells in a battery with SOCs, let's say 50 and 60. So their average SOC will be 55%. Now what will be the standard deviation for this first one? It will be minus 5 by 10. Here the standard deviation will be plus 5 by 10. Now let's say you want charging. So this standard deviation is used as the balancing factor. Now, let's say you are charging the batteries, then which SOC you want basically, you control here the charging rate. So while charging, depending upon balancing factor, you control the charging rate. So the positive standard deviation while charging will be charged at a slow rate, and the negative standard deviation will be charged at faster rate. Just a second. Hello. जी. हाँ, बताइए जरा. हम्म. नेक्स्ट बिलिंग साइकिल तो अभी दूर है, मुझे थोड़ा अर्जेंटली ये कैंसिल करना था. तो हम्म. तो वो तो सेटल सेटल तो हो चुका है ना, जो ड्यूज तो मैंने पेमेंट कर दिया था. हम्म. तो मतलब मुझे समझ नहीं आया, तो क्या करना है आप बोल रहे हो? मतलब अगर हो चुका है पेमेंट और सब, तो ये नोडी सर्टिफिकेट क्यों जनरेट करना है? ठीक है, नहीं थैंक यू. यस. तो depending upon the standard deviation, basically we charge at a slower or a faster rate to achieve the equal SOCs for all the cells. Similarly, while discharging, if you have positive standard deviation, you will discharge at faster rate, and if you have negative standard deviation, you will discharge at slower rate. After that, we come to the EV charging infrastructure. So there are various modes of operation for this EV charging. So the first one, the mode one, is the simple, where you have the plug point and you are connecting your EV to it. And in the second, in the mode two, you are charging it, but you have a control pilot in between to control the charging or discharging process. In the mode three, you have this EV charging supply equipment. So here what you can do is basically you can use this to charge or discharge not only from the power socket that is available, but also from maybe from other EVs or other devices. That it is a expensive equipment. And in the mode 4, basically you are charging from the EV charging station. And again, it can be of AC type or DC type. And depending upon this, there are different. You can see the architecture of the plugs is different. So since the battery will be charged using DC power, so if you use a DC charger, it will result in faster charging. Now, you see how is the architecture of a EV charging system. So here, basically, the user is having a mobile application, and using that mobile application, it is giving the information to the charging management system. So various information such as the initial SOC or the current SOC of the EV, then the final or the desired SOC after charging that it wants, then uh, time of charging, that is for how much time is the vehicle available for charging. Then it may also give the desired price of charging. Now, once all these features are input to the charge management system, so the charging management system will decide that at what charging rate, at what charging rate, at what price, charging duration or interval. So these all will be decided by the charging management system, and the EVs will be charged through this EV supply equipment. So the charging will be done and the EV is finally charged. So this type of setup you can basically find in offices or in malls, shopping malls, or in a very large society. So the benefit here is basically what happens. You can see that let's say you two cars have come for charging. So the first car, the initial SOC is 70% and the final desired SOC is 100%, and the time for which it is going to be parked, let's say it is 5 hours. Let's say a second vehicle has arrived with SOC 30% and its desired final SOC is, let's say, 90%, and let's say it is parked for 2 hours. Now, let's say you see this second vehicle, it has to charge for greater capacity, right? It has to charge from 30% to 90%, but the time available is less. So what this charging management system can do, it can charge this EV with EV1. So basically the power, this EV2 can be charged from EV1 as well as from the power supply or the grid so that it can be charged to the desired level within the short amount of time. Now, after this has been charged, then since the SOC of the first it is having more time, then you can charge the EV1. So EV2 is charged first and then you can charge EV1. So hence when you have large number of vehicles with you, such type of facility can help in greater basically social welfare among the EV users. And they can also provide services to the grid. Let's say similarly, this was the vehicle to vehicle operation. Similarly, they can also do vehicle to grid. Let's say if they are parked for large number of hours, they can even give power to the grid to support the grid operations. Yes, the FOC of let's say as a EV2 is coming and it is saying that I will be parking for 2 hours because it may have the user may have some other work to do and it is telling that 90% SOC. So if EV1 was not there, then what the charging station it will tell? It will tell that it is not possible to charge your vehicle up to 90%. Maybe in 2 hours I can charge you up to 60%. So now, but since the EV1 is already present, so it is taking help from EV1 and it is able to charge up to 90% in the less amount of time also. Yes, because through this EV1 battery, EV2. So a series parallel, a direct connection between them. I don't know this basically EV supply equipment will have the multiple charger port which will facilitate the charge transfer, I guess. It is not that directly you connect the battery, you connect it through this supply equipment. So this are some smart charging concepts are there for the optimal EV integration. So the time of use pricing without automated control. So again here that depending upon the grid prices, so you are trying to charge or discharge your EVs, like we have seen for the batteries also. So basically when the grid prices are low, you would try to charge your EVs during that period of time. Then in the basic controlled on off, so you are not basically bothered about the grid prices. According to your utility, your comfort, you are just switching on or off your EV. Then in the bidirectional control, what you are doing is basically you are doing both from vehicle to grid as well as from grid to vehicle. Means bidirectional power is given to the grid and also it is injected and absorbed from the grid. So there are different types. Either the vehicle can be used to give services to the grid, or it can be used for using the critical as a backup for the home, basically. Let's say you have charge in your EV and the power cut has been there in the home, so you can use that battery for your home application also. Similarly, vehicle to building also is the same thing. Then vehicle to load, basically, if you want to charge any critical specific load in your home, such as maybe water pump or some medical equipment. So that is then your vehicle to load. So smart charging concept for optimal EV control. So here basically you have the battery. You can see here you have the EV battery. Then you have the BMS, basically the battery management system. And the battery management system is communicating with the charge controller. And here basically this is your uh, grid which is used to charge, and this conversion AC to DC, and here you are using AC voltage. This is converted here to DC, and then you are using various protection circuits to basically charge this battery by communicating through the charge controller and the battery management system. Now, limitations of the fast charging. Fast charging were, it may lead to uh, higher overall losses, and it can also reduce the lifetime of the battery if you are always charging at very fast rate. Then it can also create lag between voltage and state of charge, and also you need thicker cables if you are charging with faster rate. Lastly, the last concept was hierarchical control in the hybrid AC-DC microgrid. So we have seen the structure of the AC-DC microgrid in the last lecture, I think, last or previous to last. So there, the various components were the intelligent electronic devices, various converters, then various AC and DC sources and loads. Then there was the bidirectional converter or the interlinking converter. Now, depending upon the application, we had three structures: only AC coupled, or only DC coupled, or we had a hybrid AC-DC coupled. Then we also saw that what is the need for storage in this type of microgrids, because to handle the intermittencies of the renewables. Then the various management techniques, such as your power management techniques or energy management techniques. Then we have seen the classification of control. We had seen decentralized control, distributed control, and centralized control. So we had discussed that decentralized control was the fastest, and this was the primary one. Here, no communication was there between the devices, and the disadvantage here was that it may not reach to the global objective since there is no communication. No global objective. In the distributed control, it was the secondary layer. There is communication between the devices, and the converters. They are sharing the local variables to reach the global variable or objective. And lastly, it was the tertiary, was the centralized one, and it was again communication was based there. And here you are optimizing to meet global objective. And the disadvantage here was single point of communication failure because everyone is communicating to the central control station. And if that central control station fails, then you have this single point of communication failure. So if you see the hierarchical control architecture, the primary control, so this is the fastest. This is the primary one. And the operating time is between microsecond to millisecond. So here the type of control you are doing is either PQ control, VF control, island detection, or protection. Then in the secondary control layer, you have the time of operation between seconds to minutes. And here either you are dealing with the synchronization or power quality issue or the voltage frequency restoration. And then lastly, the slowest control loop from minutes to hours is the tertiary layer. And here you are communicating either with the grid operator or with the energy market. And you are dealing with functions such as power exchange, optimization, unit commitment, optimal dispatch, or demand side management. So this brings us to the Q&A session. So the rating of the DC input capacitor should be less than grid voltage, equal to grid peak voltage, greater than grid peak voltage. Greater, yes, to basically ensure that power flows from to the grid side. The function of the bleeder resistor in an inverter is to discharge the energy stored when inverter is not in operation, equalize SOC through passive balancing, both A and B, or none of these. No, if we invert, hmm, so that will be to discharge the energy stored when the inverter is not in use. Now, DFIG is which type of machine? Yes, yes. The number of cells connected in series provide high current or high voltage. Yes. Passive balancing possess small size, high size, small or bulky, cost low, high, charge is wasted or not wasted, balancing is slow or fast. So it is small size. Then cost will be low. You don't have any controller there. You just have some resistor and few switches. Then, but charge is wasted because you are basically dissipating it in the form of heat through the resistor, and it is then slow balancing. Slow means how much time is required, because dissipating in the form of heat will take time, no? Hmm. Small size, low cost. See. When the battery is being charged, the terminal voltage decreases with increasing charging rate, increasing state of charge, increasing temperature, all of the above. Increasing temperature. In both of these, the voltage increases. Charge rate means basically at how much, like 5 coulombs per second. So this is the charging rate. And increasing state of charge, that is the SOC. When the SOC will be 50% to 60%, then what will happen to the battery terminal voltage? It will also increase. And if you try to uh, this charging rate, basically if you try to charge it using a faster charging rate, then also that, because in both the process you are basically charging the battery, so the voltage will increase across the terminal voltage. Why cannot we have an onboard charger in a DC fast charger? So obviously, first thing is we saw that this fast charger was requiring cables with more like thicker cables, so it will be more expensive, and due to that, it will also occupy more space because you're adding another component to the EV. So it will again add to the space, and it will also not allow the charging between multiple users. So it is actually all of the above. Now, what is the aim of Droop controller in an AC-DC hybrid microgrid? Maintain frequency or maintain voltage? Yes, maintain frequency. Then at frequency means at the AC side. Now, the interlinking converter enforces which of the following? No, it is the bidirectional converter. Between this, in one side you will have a pure DC microgrid, and in other side you will have a pure AC microgrid. And between them you will have a interlinking converter. So it will try to basically match the voltage here and the frequency here. It will try to equalize that to maintain the synchronism. So in per unit, it tries to do this. Because in one side you have pure DC microgrid, and in other side, this is the third type, the hybrid AC-DC configuration. Hmm. The short-term system operating conditions are maintained by power management strategies or energy management strategies, both or none. Short term is actually power management. The in the long term, we are concerned about energy. Supercapacitors are a type of capacity oriented or access oriented storage. So whether they are a high power type or high energy type. No, actually supercapacitors are high power type. Means they can charge or discharge in very small amount of time, but they cannot store the large amount of energy for longer period. That means it has high power but low energy, and high power type are the access oriented type. Yes, a charge or discharge very quickly, like very rapidly in small amount of time, it can charge or discharge, but it cannot store the energy for longer period of time. Like for that, for storing the charge for longer duration, we have this high energy type, which is done by your battery energy storage, basically lithium ion batteries. Uh, I think I have a few more questions. Just, I think I have one, two questions. Previous year assignment questions, or these are previous year assignment questions only, and I think we have discussed like purpose of PLL is to track grid voltage magnitude and phase angle, or track grid voltage magnitude, track grid voltage phase angle, or track the grid frequency, which is correct. Yes. Then DFIG was a slip ring type. Then what is or other? That I told no that VOC is greater than VPV and ISC is greater than IPV. I think this is the correct, but I will again check in the book and see. You were saying that this option is not available in the current assignment. Hmm, but it should be this only. EV charging standard. Uh, what were the standard? Was it something like ISO 15118 123, ISO 118982, IEC 62840? Were these the numbers? So these are not the standards. If anything, these are not the EV charging standards. So if anything except this is there, it is correct, or otherwise none of this will be the answer. No, these are not the EV charging standards. Oh no, these are the standards. Sorry, sorry. These are the standards. Sorry. Yes, yes. Working principle in the sense, I think that we will see in the next class also. Basically, it will act as a bidirectional converter, and it will basically either you have one side AC, then you have this interlinking converter, and you have a DC side. So if there is excess power here, then you want the power to flow from DC to AC side. Then this interlinking converter will act as a DC to AC converter, so that power flows from this side. And similarly, if you have excess power generation from AC side, you want the power flow in this direction. So depending upon that, basically this capacitors voltage and all will be controlled. That power flow is in this direction. Frequency. Hmm. Cell imbalance, I think we discussed now, maybe due to differences in the temperature, differences in their internal resistance, differences in leakage resistance, difference in system. Huh. Hmm. Internal resistance is, acha, it is not temporary. Internal resistance will be always present, no? So it will be permanent. Next, no, here you only cell to cell is active balancing. No, shunt is passive. So all are incorrect, I think. Okay. Mm. Private entities coming to. Mhm. So it will, if it wants to operate always in grid connected mode, so grid will always be in AC. So for that, it will be simpler if it is in a only AC coupled microgrid. So that you don't, once you are in synchronism, then if you have DC coupled microgrid with the grid, then you need to have sophisticated converters to basically match for synchronism and also for power conversion. But if you have a AC coupled microgrid, you can directly add the AC bus to the grid. Hmm. Hmm. Yes. because the cost of converters and all will be minimized there, and sophisticated controls will also be not required. Okay, thank you, sir. Then we'll meet in next week for the week 10 discussion. Thank you for joining.